We now take a look at another example of intrinsic linear regression. The B column shows the x-coordinates, which is the distance from the Sun, more accurately the semi-major axis of the 8 planets from Mercury to Neptune, expressed in millions of kilometers. And the y-coordinates will be the number of years that it takes for each planet to orbit around the Sun. So clearly Earth takes 1 year to go around the Sun. Mercury takes 0.241 years to go around the Sun, while Neptune takes 164 years to go around the Sun. Let's plot the scatter diagram here. So if I go Insert, Scatter, and choose this. Actually, I don't want to do that. Let me choose Insert, Scatter without the line. And if I fit the trend line, if I try to fit a linear fit, we see that we do get a value of r that is pretty close to 1. R squared is 0.9763. However, we can see immediately that the fit here is definitely not linear, that there's a curve to the graph. One way of seeing this is that the y-intercept of this line is negative 8.797. 8.797. Clearly, we can't have a negative number of years that it takes a planet to go around the Sun. So the linear fit here is clearly inappropriate. It's missing an essential physical characteristic of the problem. A second thing that we can see is that the data is definitely curved. The ones on the left side are on one side of the line, so these are all above the line. In the middle, these are all below the line. And on the very end here, this one is above the line. So the data is curved. It goes above the line, then below, and then above. The technical term for this is heteroscedastic. Basically, it's a funny way of saying it's curved. The residuals, the distance from the line, depends on whether it is to the left or in the middle. Ideally, the residual should be basically random chance if it's above or below the line. Here there's a definite trend. The ones that are far away are above the line, and the ones that are in the middle are below the line. So for both of those reasons, the fact that it's unphysical to have a negative number of years to go around the Sun, and also the fact that the data is clearly curved, we think this linear model is inappropriate, even though the value of r squared is quite close to 1. So that's not the model we want. What we're going to do instead, let's see. So what we're going to do instead is not model this with a linear fit, but with a power law fit. Now the power law fit will have the form y is equal to a times x to the b. That's called a power law fit. Now that is not a linear equation. So to get a linear equation, what we will do is take the log base 10 of both sides. We could take natural log of both sides, basically just the logarithm of both sides. So that's equal to the logarithm of a times x to the b, base 10. And then using the laws of logarithms, that's equal to the logarithm of a base 10 plus b times the logarithm of x base 10. Now this is a intrinsically linear model if I make a transformation. So what I'm going to do is I'm going to let y prime be equal to the logarithm of y base 10. And I will also let x prime be equal to the logarithm of x base 10. And then this equation therefore becomes y prime is equal to a constant logarithm of a base 10 plus b times x prime. So this is now an intrinsically linear model. Y prime is equal to constant plus another constant times x prime. Okay, so let's program this in Excel. So first off, we need x prime and y prime, the transformed variables, and those will be equal to the log base 10 of each number. And so just filling the pattern, we get these values for x prime and y prime just by taking the log base 10 of everything. So the log of 1 is 0. The log of 160 something is going to be 2 point something because the log of 100 is 2. The log of 4,000 something will be 3 point something because the log of 1,000 is 3 and the log of 10,000 is 4. Now if I plot these new transform variables against in a scatter plot, these clearly fit a linear pattern. And if I find the equation of the trend line for this data, so I'll add the trend line. Linear fits, display the equation on the chart, r squared. Here we see that the data definitely is linear. We get y is equal to 1.4998, basically 1.5, minus 3.2618. And let me add a few extra places just to see how close this r squared value is to 1. So let me take, say, 8 decimal places. And we see that the value of r squared is very, very close to 1 indeed. Not exactly 1. It's not exactly on a straight line, probably due to measurement error or just simply round-off error, but it is indeed very, very close to 1. Okay, so there is our equation. So let's put that on right. Let me write that down. So I'm going to take this off screen and then write down the result. So our result is that y prime is equal to log of a, the constant term is negative 3.26180826 plus basically 1.5, and I'll just simply round it off at 1.5 times x prime. Okay, so now we have to figure out what a and b are. Well, we see that the b is 1.5, that these match, so b is going to be equal to 1.5, and that log of a is equal to this. And therefore, if the logarithm of a, base 10, is equal to negative 3.261808, then a itself would be equal to 10 to that power. So 10 to the negative 3.261808. Which is 5.47, let's round it off to 3, times 10 to the minus 4. And so going back to the original equation, we get that our model is finally y is equal to 5.427, or 5.473 times 10 to the minus 5, or 10 to the minus 4, pardon me, times x to the 3/5 power, or 3/2 power to the 1.5. And this is actually a statement of Kepler's law of third planetary motion. If I were to square both sides, we would see that the cube of the distance from the origin is proportional to the square of the year for the planet. And so this is a confirmation of Kepler's third law of planetary motion. Before ending this video, let's talk about how to do this on a calculator. Actually, I'll show. Actually, before I do that, let's go back to the original data. So let me close this out. And if you notice, let's go back to the original data. Insert scatter. And let's add the trend line. Now you notice here that there are different options that are available for plotting a trend line. One of them is the power law option, which we just discussed. And so if I display that on the chart, we get exactly what we just had. So let me add a few extra decimal places. And we get, I hope, the same numbers that we had before, 0.000547, and then x to the basically 1.5 power, 1.49977. So we have the same numbers that we had before, so Excel does that computation for you directly. So if it's built into the calculator, by all means use it. If, however, we have a formula that is not built into the calculator, then you need to be able to do the kind of algebra to be able to change an intrinsically linear equation into a linear equation. Finally, let's talk about how to do this on calculator. So we have over here we have stat edit, and so I've got the same 8 pairs of data over here. So as before, we'll let this list be equal to the logarithm of the first list. So those are all the logs in list L1. And we'll let L5 be equal to the logarithms in list L2. And then I go to stat calc. I will do a linear regression on L4 and L5, where L4 are my new x coordinates and L5 are the new y coordinates. And so doing a linear regression on that, I get hopefully the same numbers that I had before, 3.2618. That is the intercept, or negative 3.2618, that's the intercept. And the value of b matches what I had before, 1.49977. The TI calculator also does power law fits. So if I go to calc and then go down a ways, down here is the power regression. And for this one, I would use the original L1 and the original L2. And that would give me the numbers that I have here, 5.473 times 10 to the minus 4. And the exponent b is basically 3 halves, 1.49977. So if the function is built into the calculator, by all means use it. If the function is not built in, then it is your responsibility to be able to use your skills from algebra to be able to transform it from an intrinsically linear function like y equals ax plus x to the b to something that is intrinsically linear like the one in blue.